Okay, so hey everyone, I'm Brian, and as part of the first Geometric Analysis Festival, I'm here to give you a talk on singularities of the inverse mean curvature flow. One thing you'll notice from this title is that I decided to experiment a little bit with the format for this slideshow, so I hand wrote some notes and put them into a slideshow. I should warn you that I needed to resize some of these notes for some of the slides, which might make some of the slides a little bit difficult to read, but I don't think that this should be a problem if you go full screen on the video. And let's begin. Okay, so this is going to be a talk about extrinsic geometric flows, all for closed surfaces, as in compact and without boundary, all in Euclidean space, and all codimension 1. Now, the basic idea behind an extrinsic geometric flow is you have some surface and you deform it in the normal direction. And the speed of the deformation somehow depends on the principal curvatures at each point along the surface. So the most well-known example of an extrinsic geometric flow is the mean curvature flow. And for mean curvature flow, the speed of the deformation at a given point equals the mean curvature at a point. So if you have an initial surface m0, you're trying to solve for a one-parameter family of surfaces which satisfies flow velocity at each point equals minus h times the outward unit normal. And each of these flow surfaces can be realized as the image of some time-dependent immersion for the same underlying closed manifold M. So that's the basic idea behind mean curvature flow. And just to keep an example in your mind, mean curvature flow is a contracting flow. So if you start with, say, a round sphere of radius r, mean curvature flow will shrink it to a point. The radius of the sphere at later times will be r of t equals square root big R squared minus 2nt. Now, some natural reasons you might be interested in studying mean curvature flow are first that it models many physical systems. This isn't going to be the focus of the talk, but for example, grain boundaries and annealing metals, as well as surface tension phenomena are modeled to some approximation by mean curvature flow. Many applications to the geometry and topology of surfaces, for example, similar to what Perelman did for the Ricci flow, applying it to the Poincare conjecture, you can also apply mean curvature flow to classify the topology of surfaces in Euclidean space. And maybe the most natural motivation, just kind of pure math motivation for mean curvature flow, is that it's the L2 gradient flow for the area functional. So if you take the area of a given surface, M, mean curvature flow will not only shrink that area, but it will shrink it in the most efficient way possible. And this sort of makes it a very natural analog to the heat equation, since the heat equation does the same sort of thing for the Dirichlet energy. So mean curvature flow is sort of the canonical contracting flow, but it will not be the focus of this talk, as the title implies. For this talk, I want to focus on expanding flows, and specifically the most well-known expanding flow, which is inverse mean curvature flow. So inverse mean curvature flow is an outward directed flow. You take an initial surface that has positive mean curvature everywhere. This is something that didn't qualify here, but all of your flow surfaces need to have positive mean curvature everywhere. And you deform it in the normal direction, and you require that the flow speed of the deformation at each point is equal to 1 divided by h, where h is the mean curvature at each point. So this is why you need positive mean curvature, because you can't have a 0 in the denominator. So it can't be just like positive at some places and negative other places. But so it's a purely outward directed flow with flow speed 1 over h. And you should expect it to expand things off to infinity. And I actually just wanted to mention first, before I mention the motivation up here, I want to draw your attention down here to an example. So if you take a sphere with initial radius r, a round sphere, mean curvature flow will expand the sphere off to infinity. the radius as a function of time of the expanding sphere will be big R times e to the t over n. So you have exponential growth in the radius and also exponential growth in the area. Exponential growth in the area is just a generic feature of inverse mean curvature flow. Okay, so that was down here. Let me say up here a little bit about why people study this, this flow. So being an expanding flow, it doesn't arise naturally from a variational principle like mean curvature flow does with area. I will have a little bit more to say about variational formulations for this flow in a little bit, but let's just say now that's not really the reason that people study it. Either way, it has many applications in geometry and topology. For example, you have tons of geometric inequalities coming out of studying the inverse mean curvature flow. And probably the highest profile of these is the Riemannian-Penrose inequality in general relativity. So I didn't fully qualify everything that I meant when I wrote this inequality down here, but if you have an asymptotically flat Riemannian manifold and you consider its outermost minimal surface sigma, what the Riemannian-Penrose inequality says is that you can bound the ADM mass of the metric G on M by below by something that only depends on the area of this outermost minimal surface. The ADM mass, obviously I can't completely elaborate on at the moment. It's roughly an invariant of asymptotically flat manifolds, but it technically does depend a little bit on coordinate systems. This is just background if you want to read more about Huisken and Neumannen's proof of this using inverse mean curvature flow. So again, this will not be the focus necessarily of the talk. The focus will be on singularities of the inverse mean curvature flow, which there isn't really a lot of literature on. So I want to talk about formation and characterization of singularities for the inverse mean curvature flow. And of course, singularities for mean curvature flow are a very well-studied topic. So there's two elementary results on singularity formation for mean curvature flow. On the level of formation, you know for mean curvature flow that singularities of closed hypersurfaces always form. And this is actually an immediate consequence of the comparison principle. If you take an initial surface M naught and you evolve it by mean curvature flow, you can just surround M naught with a round sphere, which of course will contract to a point under mean curvature flow. Well, if the ambient sphere contracts to a point, this should imply some singularity for the evolving surface MT before this happens. And not only does this tell you that singularities always form for mean curvature flow, it also tells you that they form within a prescribed time interval that only depends on initial data. So you know that the singularity starting from M naught needs to happen within the time extrinsic diameter of M naught squared divided by 2n. And on the question of characterization for mean curvature flow, you know that singularities are always characterized by blowup in the total curvature. So the total curvature, norm A, is the square root of the sum of the squares of every principal curvature. And you know that any singularity of mean curvature flow is characterized by blowup in this quantity somewhere along the surface. And the reason that this is true is essentially because of parabolicity. So you can get that if this quantity is bounded, then the limit surface one obtains at a particular time will be completely smooth, and this allows the flow to continue. So these are the two results to keep in mind for mean curvature flow. You always have singularities forming in a prescribed time interval, and they're always characterized by blowup in at least one of the principal curvatures as you approach the singular time. So how does this picture look different for inverse mean curvature flow? Well, for one thing, singularities under inverse mean curvature flow don't always need to develop, as you saw with the round sphere example. So Gerhardt showed that this is actually a more general behavior for inverse mean curvature flow. If you take a positive mean curvature and star-shaped hypersurface and you evolve it by inverse mean curvature flow, the flow actually exists forever. And also the sphere is stable under star-shaped perturbations. So in other words, if you take an initial surface nt and you rescale the surface, or you blow it down by e to the minus t over n, the rescaled flow surfaces will become more and more round as one approaches t equals infinity. Okay, so singularities don't always need to form for inverse mean curvature flow. However, they can in some cases. So the most well-known example of singularity formation for inverse mean curvature flow is if you consider a thin torus. So that is a torus where this inner radius is small enough that the entire torus is mean convex. Inverse mean curvature flow will puff this torus out with some flow speed that's bounded below by initial data. And what that means is that what we should expect is mean curvature goes to 0 along the inner ring as the torus expands. If mean curvature flow goes to 0 along the inner ring as the torus expands, the flow speed 1 over h is blowing up along that inner ring, and that causes a singularity. So blow up in the flow speed 1 over h is actually a generic feature of every singularity for inverse mean curvature flow. So if you have a solution to inverse mean curvature flow, what Wiskin and Ilmanen showed in 2008 was that the minimum value of the mean curvature is going to 0 as one approaches the singular time. So of course, for mean curvature flow, sort of the only obstacle to the flow existing forever is blow up in the total curvature. Inverse mean curvature flow, you have to worry about blow up in the total curvature or mean curvature going to 0. And what Wiskin and Ilmanen showed is that if you do have blow up in the total curvature, you must also have mean curvature going to 0. So singularities will always be characterized by this happening. Okay, so now that we've seen this thin torus, I'd like to raise 2 questions to do with this singularity. So this, and not in the last slide, didn't have spherical topology. The singularities always form for things without spherical topology. And if so, do they form within a prescribed time interval that depends only on initial data? Because this is true of mean curvature flow. So this is the formation question that I'd like to focus on for inverse mean curvature flow. And the characterization question that I'd like to focus on has to do with blow up in the total curvature. So as I said, if you think back to this picture, you should have mean curvature going to 0 eventually along the inner ring. As mean curvature is going to 0, a natural question is the total curvature along the inner ring blowing up? So put another way, if you consider the axis of rotation for this torus, does the inner ring reach the axis of rotation by the singular time? So that you have like one curvature, this one going to minus infinity, and like this one going to plus infinity as the singular time is reached. Does that happen, or does the flow terminate before this ring is completely filled? So I'd like to ask this in the context of the thin torus, but perhaps it generalizes. Perhaps, whatever we can figure out about the norm of A, near singular times we can generalize. Okay, so I'm going to answer each of these questions just in brief right now. And then after that, the rest of this talk will focus on how I obtain these solutions. So on the question of formation, the answer to one is yes, you always have singularity formation within a prescribed time interval if the solution is embedded. But this is actually a corollary of a more general statement about inverse mean curvature flow. So in a paper that I wrote last year, I found two alternatives. If you consider any solution to inverse mean curvature flow, one of the two following possibilities happens. Either the flow exists for all time, the flow surfaces are embedded for all times, and they're star-shaped beyond a certain time, which depends only on initial data. So this time t star that I wrote here is equal to 2n times the natural log of lambda max. I didn't write down the definition of lambda max here, but it's the largest initial principal curvature of n naught times the diameter of n naught. Okay, so this is a quantity that depends only on n naught. And what I'm saying is that like either the flow exists for all times, it's embedded for all times, and it's star-shaped beyond the time t star, or the flow either goes extinct or it self-intersects within the time t star. So this would be the analogous statement to mean curvature flow, where you have, in this case, either finite time extinction or self-intersection within a prescribed time interval. Something I'll mention if you know a little bit about mean curvature flow is also that you couldn't have self-intersections for mean curvature flow, but you can certainly have intersections here. But my point is that if either of these things happen, they happen within a prescribed time interval. And if they don't happen, you will be star-shaped beyond a specific time. Now, once a surface is star-shaped, it has spherical topology. And if it's embedded for all times, that means that it started with spherical topology. So if you start with a surface that doesn't have this topology, it needs to satisfy B rather than A. And that's why I said that the answer to 1 is yes for embedded solutions. Now, what about the answer to 2? So 2, the answer is that you don't necessarily have blow up in the total curvature near the singular time. And this is true for the torus that I showed you earlier, but it actually turns out that it's true for any rotationally symmetric embedded torus. So if you take a mean convex rotationally symmetric embedded torus, I verified first that you do get a finite time singularity, but then I also showed that the total curvature is bounded near the singularity. Now, from the point of view of parabolic PDE, this is very odd because what it's actually is telling you is that the flow surfaces NT will converge to some sort of limit surface NT max as one approaches the singular time. So somehow you get this nice, well, might not be perfectly smooth, but at least some sort of limit surface without rescaling the flow surfaces, but you cannot continue past the singular time from this flow surface. So those are the two main results that I'd like to spend the rest of this, this session talking about.